Oxygen dissociation curve. It is the sigmoid-shaped curve plotted with oxygen tension on x-axis and oxygen saturation on y-axis. So there are some important points on this curve. First is the arterial point. It is the oxygen tension of 13.3 kilopascal at which oxygen saturation is 97 to 100%. Then there is mixed venous point of 5.3 kilopascal of oxygen tension at which oxygen saturation is 75%. There is reference point called as P50, which corresponds to 3.5 kilopascal of oxygen tension and 50% of saturation. So the oxygen saturation increases with increased oxygen tension. The steep gradient in the middle portion, it is due to cooperative binding of oxygen to the hemoglobin. At high oxygen tension, reduction in the oxygen tension leads to small reduction in the oxygen saturation. At low oxygen tension, small reduction in the oxygen tension lead to higher reduction in the oxygen saturation. It corresponds to the steeper part of the oxygen dissociation curve. In peripheral tissues, oxygen tension is low, that is, the steeper part of oxygen dissociation curve. Therefore, reduction in the oxygen tension leads to large offloading of the oxygen. With the oxygen content formula, we can calculate the oxygen content of the arterial blood, which is 20 ml per deciliter. Oxygen content of mixed venous blood is 15 ml per deciliter. Now we'll discuss about rightward shift of oxygen dissociation curve. In this diagram, we see that the normal oxygen dissociation curve, the arterial point corresponds to 100% of saturation and 20 ml per deciliter of blood volume of oxygen content. The mixed venous point corresponds to 75% of saturation and 15 ml per deciliter of oxygen content. When the oxygen curve is shifted to the right, the mixed venous point with the 5.3 kilopascal of oxygen tension corresponds to 40% of saturation. So, in the normal condition, the difference between arterial oxygen content and venous oxygen content, which is 5 ml per deciliter, it corresponds to the oxygen unloaded to the tissues. When the oxygen dissociation curve it shifts to the right, the difference between the oxygen content of arterial and venous blood, which is 20 minus 8, it is 12 ml per deciliter, it is unloaded to the tissues. So the conditions causing rightward shift of oxygen dissociation curve leads to low oxygen affinity favoring unloading of oxygen. There are physiological conditions like high carbon dioxide, which is called as Bohr's effect, increased 2,3 DPG, pregnancy, altitude. The pathological conditions are acidosis, hyperthermia, sickled hemoglobin. Now we'll discuss about leftward shift of oxygen dissociation curve. In this diagram, we see that the normal oxygen dissociation curve, the arterial point corresponds to 100% of saturation and 20 ml per deciliter of oxygen content. The mixed venous point corresponds to 75% of saturation and 50 ml per deciliter of oxygen content. When the oxygen dissociation curve is shifted to the left side, the venous point of 5.3 kilopascal, it corresponds to the saturation of 90% and oxygen content of 18.2 ml per deciliter. So in the normal conditions, when the difference between oxygen content of the arterial and venous blood is 5 ml per deciliter, which corresponds to the oxygen delivered to the tissues. In the leftward shift, the difference between arterial and venous content is 2 ml per deciliter. It means that the conditions which causes Left shift of oxygen dissociation curve have high oxygen affinity favoring binding of oxygen, and it leads to less unloading of oxygen to the tissues. The physiological conditions are low carbon dioxide, fetal hemoglobin, reduced 2,3-DPG, and pathological conditions are alkalosis, hypothermia, carbon monoxide, and methemoglobinemia.